Okay.
Oh. It is okay. Is that better?
Yeah.
Okay. Yeah, I'm good.
Okay, cool. Hi, everyone. We are very lucky to be joined by Jacob Steinhardt today. Jacob has done like a bunch of really important work in sort of trustworthy machine learning broadly understood, including both a bunch of the early work on adversarial robustness and also on kind of representations of truthfulness in language models, interpretability generally, and today some work on automating some of that process and using language models for interpretability as well as scientific discovery. So we'll go from there. As a reminder, we also have the normal EI seminar happening again on Thursday, so come back then for, I can actually remember who's presenting. Okay. Last name. Okay. For an internal talk, details of which are going to be shared soon. And yeah, I'll hand it over to Jacob.
Cool. Yeah, thanks very much for having me and for coming at the non-standard time. I'm really excited to be here and to learn about all the work you guys are up to as well. So today I'm going to be talking about using large language models to understand a bunch of things, but in particular other large language models. So to give kind of the motivation here, right? Actually, can people hear me like this, or should I stand in front of the?
This is why people will not be.
Okay, how is this better? Yeah. Okay, great. So, right. So, kind of the motivation here is, LLMs and other frontier models are, doing lots of amazing things, but we're kind of, there's not just like one of them. We're getting like a new one, basically every couple months. And they often exhibit new behaviors that the previous iteration didn't. And they're being deployed in a very broad variety of use cases. So to really understand them in a way that could let us, for instance, like anticipate possible failure modes, or even just kind of like get good scientific understanding of what they're doing, we kind of are in this cycle where we're always playing catch up, right? Every couple of months, a new model comes out. We have to understand it. Probably by the time we've even started to understand it, the next model has come out. And so how can we kind of break out of this cycle and get some more kind of scalable methods to get understanding? And so the kind of key perspective that I'm going to take in this talk is we could actually, use LLMs as explanatory tools to aid our understanding of, I guess, maybe data in general, but in particular data about what machine learning models are doing and how they behave. This would create kind of a virtuous cycle where every time a new LLM comes out, we have better explanatory tools, and so then this helps us with our understanding. And so that's going to be kind of the perspective in this talk, and I'll kind of showcase this perspective through several different case studies. The work I'm going to be talking about was done with many collaborators and colleagues, but in particular. With large contributions from these three PhD students at Berkeley, Erik Jones, Ruiqi Zhong, and Yossi Gandelsman. So I guess to be a bit more concrete about how we're going to get understanding, I'm going to take the perspective that many forms of understanding that we want can, in some sense, be reduced to statistical learning or some form of data science. So just to give examples of this, right, if we want to understand things about a model's behavior, essentially what are we trying to do? We're trying to kind of identify meaningful patterns that generalize across many different settings. And that's basically a statistics problem, right? We're kind of trying to find patterns in data that we can then verify. Aside from the behavior, what else matters for understanding a model? Well, the other thing that's going to matter a lot is the data used to train it. But then again, we're kind of trying to understand what are the important sources of variation in that data? Are there maybe sources of variation that are important but that we're missing that are going to lead to spurious cues? Again, this is kind of a data problem and a statistics problem. And then you could even go further and say something like, well, I have a new model. Maybe I'm like worried maybe like I'm going to use, maybe it's like a vision model and I'm going to use it for some self-driving car setting. And I'm worried that, maybe in some like new weather setting, things are going to fail, but I can't think exactly about what the failure might be. Now this is like an active learning problem where I'm trying to kind of elicit examples that get at some behavior, right? But I can still sort of think of this as statistics. So kind of if we can get LLMs to do these sorts of statistical tasks, then we can tackle these problems and get the understanding we want. And so throughout, I'm going to sort of, what do I mean by doing statistics? I'm going to think of it as, performing this pipeline. This is maybe a very schematic form of what statistics is, but we need to be schematic so that GPT-4 can do it for us. So it's going to have these sort of 4 steps, right? You look at some initial data, which in many cases we might call the training data. We form some hypotheses about that data. And then once we formulated these hypotheses, then we need to sort of formalize them into something that we can test quantitatively. And then we actually go out and actually test it by looking at held out data, or maybe even looking at generalization to some out of distribution test set, right? So this is sort of what statistics looks like. And so we're going to get LLMs to do this. But the kind of twist here is, and sort of the key difference from maybe traditional statistics, is that this hypothesis H, rather than being some mathematical function, is going to be some natural language string. Why do we want it to be a natural language string? Well, first of all, that like LLMs generate natural language strings, so it's sort of a better fit. But also, if we actually want human understanding, then we want language rather than just some black box neural representation, because then we can actually understand it. And so what is this going to mean in particular from the perspective of this pipeline? It's actually going to mean that this third step is going to be kind of like the conceptually hard step. Normally this is like an easy step. You're just like testing whether something's true. But here, like, what does it mean for some like sentence to be true of a data set? Now I need to actually, I need to kind of like formalize that mathematically. And so we'll see some examples of how to do that. So that's kind of some abstract high level stuff. If you're happy with that, good. If you're not happy with that, that's fine, because now we're going to talk about something very concrete, which is one particular use case of finding failures in the CLIP multimodal embedding model. So CLIP is a model that is kind of the backbone of many of these text-to-image models that you might be familiar with, like Stable Diffusion or DALL-E. And how does it work? It's kind of an encoder that can encode both images and text, and that's why it's useful for these kind of text-image models. And so it can do these models can do pretty cool things, right? So if I say an empty glass, I kind of get this image. If I say a family of 5 members, I get this image. A man descending a mountain, I get this image. And you kind of get these like really beautiful images and kind of really amazing results. But the problem is that all of these pictures are completely wrong, right? So this is actually a glass that's full, not empty. There's 6 people in this photo. This person is going up a mountain, not down a mountain. And there's no star in the night sky, but it's actually full of stars, right? So so these models actually have a bunch of failures. And maybe the other twist here is actually all of these failures were generated automatically via LLMs. So there was no human intervention involved here. Just to give an example, an idea of how automatic this is, during the rebuttal period of the conference this was submitted to, the reviewers complained that we were missing their favorite model. So then I asked Peter and Erik to fix that, and they downloaded the data set. That was the hard, they downloaded the new model. That was the hard part. Then they just like push a button, and a half hour later, you get all of these for the new model as well. So it really is very scalable and automated. And so what I want to tell you is like, how did we actually do this? How can we kind of automatically find these failures? So at a high level, it kind of involves a 4-step pipeline that basically mimics the kind of pipeline for statistics that I talked about earlier. So the first thing we need to do is find, take a large data set and find individual failures in the model from that data set. And we do that by finding what I'm going to call hash collisions in the clip encoder. And I'll get into what I mean by that in a second. Then we're going to categorize these individual failures into coherent patterns by using LLMs, right? By like using their ability to kind of look at data and explain the patterns in that data. We're going to test these patterns by generating new examples. And then we're going to check that these patterns don't just work kind of in sample, but like generalized to totally new domains as well. Also, feel free to jump in with questions at any point. I'm happy to take questions throughout the talk. Okay, so I'm just going to explain how each of these 4 steps work. So first, maybe a little bit more background on what CLIP is. So as I said, CLIP is an encoder model. So what does that mean? It takes an input and it embeds it as a vector. So it's not a classifier. It's not generating anything. It's used as the first stage of many generative pipelines. But all it does is take an input and produce a vector. The important thing is that it can take either images or text and produce vector representations of both. How is it trained to do this? Well, I will take a data set of, for instance, images and their captions, or any kind of image and text that's paired together. And I'm going to have a kind of contrastive loss where I want each image representation and the representation of the corresponding text to have high cosine similarity, and for all of the other ones to have low cosine similarity. So if I kind of form this matrix of dot products between all of the image representations and all of the text representations, ideally I want the diagonal to be all 1s and everything else to be all 0s. And there's some particular mathematical loss function that encodes this, but the important thing is just this idea that we want images and text that are about the same thing to have the same embedding, and about different things to have different embeddings. And so now I can tell you what I mean by a hash collision. So a hash collision would be if I have 2 different texts, T and T prime, that mean different things, but that embed to the same or to very similar points in this model. Why is that a problem? Well, if say T2 and T3 had nearly the same embedding, then I'm not going to be able to succeed in making this diagonal, right? Because all of these entries have to be the same, so I'm going to get kind of this blurring. And so I kind of know, maybe I don't know which of T and T prime is going to create a problem for me, but I know at least one of them, and maybe both of them have to kind of create problems in the sense that like the images they correspond to can't kind of be distinguished. So this is what we mean by hash collisions. And so concretely, how can we find these? Just take some large corpus of text. And so the nice thing here is we can do everything in text world. This is useful because language models are very good and image models are not so good, at least right now. So we put everything in text world. We just have this large corpus of text inputs. We embed them all under CLIP. And then we're also going to embed them under a text-only model called Distill Roberta, which is kind of for text is much better at understanding text than CLIP is. And so then we're going to find these places where CLIP embeds 2 inputs very similarly, but Distill Roberta thinks that they shouldn't be similar, right? So this ensures that they have different meanings, or at least probably have different meanings, but that they have these very similar embeddings. And so these are our hash collisions. So once we have these, and here's some examples where you get like a tall glass placing on the table and a short glass placing on the table. Ignore the grammar, data is messy, but the point is like tall and short both got embedded very similarly. So this gives us a bunch of individual failures. And so in some sense you could stop there, but maybe this doesn't really give you a more general understanding. And also it doesn't tell you anything about in a new domain, what should you expect to go wrong. So what we next want to do is we want to, yes.
Like, to what extent is this represented? I can imagine lots of reasons for sentences to be they have very different Roberta embeddings. They could have very different styles despite being the same paraphrases or paraphrases of each other. Just like use, in other ways, divergent vocabulary, or even be sort of mutually compatible descriptions of a common picture that are actually, just talking about different aspects of the picture. So is what pops out mostly like this, or what fraction is like actual semantic differences as opposed to
so good. So good question. Okay, so I guess empirically what happens if you suppose I didn't care about the Roberta thing at all and I just looked for collisions. Empirically what ends up happening, basically all of the things at the top of your list are like basically straightforward paraphrases of each other. And so what you mainly want to rule, basically what distill Roberta is mainly doing is it's ruling out paraphrases. So paraphrases tend to have pretty high distill Roberta similarity. And so we basically are just picking a threshold for the distill Roberta similarity that says paraphrases shouldn't count. And once you rule that out, you didn't have to get this lucky, but empirically, basically the large majority of remaining things are actual problems. Good question. Okay, so now we want to kind of generate some more general hypotheses about what's causing these failures. And so how do we do this? We basically just ask GPT-4 to help us. So we give it this prompt where we say, okay, I'm going to give you a bunch of data. Please remember it because I'm going to ask you some questions later. Then we give it, a bunch of the failure pairs, a bunch of the hash collisions that we got from the previous slide, and then we just ask it to generate hypotheses for us. So this particular prompt, I don't think the particular prompt is that important. Although we had an earlier version that had a bunch of unintentional grammar errors, and fixing those actually helped. But I don't think these very specific wording matters would be my guess. But basically we say, okay, I'm trying to find failures with an embedding model. Here's some pairs of sentences that are encoded very similarly, even though they're conveying different concepts. Using these specific examples, are there any general types of failures you notice the embedding is making, or any common features that the embedding fails to encode? And then, we say a bunch of other things. Maybe one important thing is please focus on differences that are important visually. And then also please explain clearly why the failure would lead to problems for future tasks. This is going to be useful later because we're going to be able to leverage not just the names of the failures, but the actual descriptions. But basically we have this prompt, and then we kind of can see what it does. And what it does is it produces a kind of nice numbered list like this. So I'm not sure how well people can read this, so I'll just read the first one out for you. So the first one says negation. Embedding models may not correctly capture the negative context in a sentence, leading to similarities between sentences with and without negation. This can result in incorrect visual representations, as the presence or absence of an action is significant in image or video generation. And so note that, aside from just saying negation, it, is actually saying a bit more about, say, okay, it's about actions in particular. So it's actually a slightly more specific hypothesis than just negation. And then we get a bunch more of these. It basically always generates this in this markdown list format, so we can programmatically extract the individual hypotheses. And so then we get a list. It actually doesn't have, you don't get that many distinct ones, but you maybe get about a dozen different hypotheses out of this. And so we kind of have these lists of hypotheses about general failures. And so now we are kind of we finished the first two stages of this statistics pipeline, right? We looked at some data, we formed some hypotheses, but now the hypotheses are not mathematical hypotheses, they are just natural language strings. So now kind of the key conceptual question is, how can we test if one of these hypotheses is good? And maybe I'll pose this to the audience first, because I think it is an interesting exercise to think through. So, how might we actually kind of test whether one of these hypotheses is really a good hypothesis? Yes. Yes.
You mean each of the 12, roughly 12 cases, you're considering each of those a hypothesis?
Yeah. So
I mean, you could have conjunctive hypotheses.
that's right. So let's say we have these 12 hypotheses, and each one individually we want to say, is this a true or false hypothesis about clip?
So intuitively, you would ask whether that feature in the natural language string is diagnostic of a good match between any of those variety of different diagnostic.
Right. Yeah. So somehow we want to ask, like, is the string diagnostic of failures? And so is there some concrete test we could do for this? Yes.
I would count the number of positions that we found and then see if they match with one of them.
Okay, right. So we could count collisions. Although, then we might be a little bit worried that we're picking up on some like spurious feature that might not be kind of causal. Yes.
Maybe generate a new characteristics of what of the hypothesis, and then test those and see if they're similar.
Okay, good. Yes. So this is what we're going to do. So, sorry, not used to this clicker. Right. So we're going to say H is a good hypothesis if it can be used to generate new failures. Like suppose we were like a psychologist and doing a psychology experiment. What would we do? We'd like get some human subjects. We'd tell them to like try to write down sentences that would make stable diffusion screw up, and then we would like also give them this like H as like helper information, and compare this to some like control hypothesis that wasn't generated from this data, but that seemed reasonable, and make sure that like the like intervention does much better than the control. And so we're basically going to do that, except humans are expensive. Also, humans might like figure out what the task is about. But language models, every time you give them a new example, you can like erase all of their previous context so that each example is kind of fresh. There's not like the only way to figure out what the task is about is actually by looking at H. So we basically do this. We prompt a large language model to generate new failures with H as context. So this prompt, sorry that it's again a bit small, but basically we say, write down a bunch of pairs of prompts that an embedding model with the following failure mode might encode similarly, even though they would correspond to different images if used as captions. Then we tell it to use the following format, right? So now this is a bit more important because, okay, I said you had these 12 hypotheses, you could extract them programmatically, but okay, I mean, for 12 things, I could also just copy paste. But now we're gonna try to get like hundreds of examples of failures. I wanna really make sure that I can just write a Python script to parse them. So I tell GPT-4 to do that. And then we give it the failure mode, and then with not just the name, but the full description. So, and then we're going to kind of, what are we going to do? We're going to test that these new things, first of all, actually lead to hash collisions. That's something we can do programmatically, but then we want to make sure these hash collisions really lead to problems in downstream systems. So we're also going to do a human study to look like to check whether these also lead to problems with like stable diffusion and Dolly. So here, I guess, is just the data for hash collisions. Let me explain this table because there's a few things going on in it. So each row is a different hypothesis that was generated by either GPT-4, or we actually also looked at Claude and GPT 3.5 as ablations. So these are the different proposer models. In all cases, we're using GPT-4 as the like generator of new failures. But we can, so this is just testing which of these are, how good are each of these models at kind of like, basically clustering the initial data to generate hypotheses. And then we also considered the choice of initial data set to scrape the hash collisions from. So COCO and SNLI are two language data sets that have a lot of stuff about visual concepts in them, but focus on somewhat different things. And so I guess what we see, first of all, is you get a fairly high success rate of hash collisions. So dark blue is around 80%. The majority of these things are dark blue for GPT-4. Interestingly, even for like the same hypothesis, larger models generate better hypotheses. So why is this? It's because the actual explanatory text after the hypothesis is sort of like richer and better grounded in the data. So that's why, like, I don't know what's a good example here. Maybe there's not like a super great example, but like, you know, like this is very light and this is darker. This is like darker than these. The other thing is that the underlying data set you use actually does kind of affect what concepts you end up with. So the model is looking at the data. I guess you could either consider this reassuring or not reassuring. It's reassuring that it's looking at the data. Maybe it's not reassuring that you're not getting good coverage from a single data set. But the overall point here is that you know, you get like reasonable success rate with the largest models, and larger models actually like do better at this task. But now let's actually push this through to like downstream task performance. So what we did here was we fed these prompts into various different text to image models or text to video models as well. We kind of, you know, you create this interface and then kind of, you know, for each of these images by hand, we labeled, you know, is this image either like about prompt 1, about prompt 2, about neither of them, or these prompts are like visually indistinguishable. And the point is this image was like randomly generated according to either prompt 1 or prompt 2, right? So this is kind of testing whether this, like if the hash collision is creating downstream problems, what it's going to do is presumably like, you know, both of these prompts, even though they mean different things, will give very similar images. So you're going to get an error here. So this is kind of checking whether you actually do get an error. And if we look at the resulting error rate, I've kind of plotted the error rate as a function of the clip similarity. So, you know, everything like in here, we would think of as a hash collision. Here, we would think of as like maybe a partial hash collision. And here, we would think of as not really a collision at all. And we kind of see above a clip similarity of 0.9, you pretty consistently actually do get failures in these downstream systems. And to give a kind of summary statistic here, about 80% of the time you get a downstream failure. If we compare this to a kind of dummy setup where we just ask GPT-4 to brainstorm hypotheses about ways that clip might fail without seeing the data, and then use those hypotheses, you only get a 20% failure rate. So the data is like really helping in a significant way. So then finally, and I think this is actually maybe the coolest part in my opinion, is, you know, once we have these, even though we got it from one domain, we can very easily apply it to new domains, right? So I can say, okay, I'm going to take this whole pipeline. I'm still going to start with COCO and SNLI, but I'm going to ask you to brainstorm failures that, you know, if applied in the self-driving domain, would create problems, and then generate sentences that are about, you know, about self-driving cars in some way. And so then you get things like, you know, the car is on the right side of the lane. This is not a green light, a yield sign. And you kind of get these kind of self-driving failures in CLIP. And so you're kind of seeing that, you know, basically because GPT-4 can kind of do this like abstract metaphorical reasoning about how a failure might translate to a new domain, just by kind of specifying that domain, you get failures in that domain. And so I think this is pretty cool. So to kind of summarize this part, right, we kind of basically just did this four-stage pipeline that I said. We had this like initial data that we got by scraping for hash collisions. We generated hypotheses by prompting GPT-4. We formalized the hypothesis as the success rate at generating new failures. And then to kind of, you know, validate this out of distribution, we kind of actively generated examples in a new domain. And I guess just one point I want to make, right, is that like if you just did this, you would get somewhere, but maybe not that far. Like a lot of the gain here is from, first of all, using multiple models kind of working together, but also like organizing the data in a way that is kind of like well structured to what these models can do. And so, you know, I think like, I guess in some ways prompt engineering, we need less and less of it because instruction tuning is getting better. But I think a thing that is actually still quite valuable, maybe this will not be true in 2 years, I don't know, but at least currently, I think a thing that's quite valuable is kind of how you structure the computation or task for the model. So are there any questions about this part before I go on to the next part? Yes, Jacob.
So if you do what you were saying before, just say it generates a hypothetical failure modes for me, what do the other ones look like?
Yeah,
So I would have guessed, given how much like human generated description of failure modes is probably in the GPT-4 training data, that's actually pretty strong.
Yeah, I don't remember exactly what they were, but they like sort of seemed like, they sort of seemed like the sorts of things that I would have come up with if I were just like brainstorming from scratch. Like they actually seemed pretty reasonable. I think when we first did this experiment, we were worried that the baseline was going to be like way too strong. So actually the 20% was a little bit, I would say it was like a little bit surprising.
But is that because it's over-generated, under-generated? I guess under-generated, you still need to, like this is just a precision.
Yeah, my guess is it's probably, and this is speculative, like I don't think we looked at this carefully, but my guess is it's some combination of over-generating and also like, yeah, you can come up with the high level idea of what should go wrong, but actually there is like a lot of work going into the like elaboration. And so I think the like elaborations are probably guiding you a fair amount. And if you're just like generating those from your prior, it's not going to work as well. That would probably be my guess, but I think it is an interesting question. I saw a couple more, yes?
So will the hallucination ability of GPT be a concern for generating those hypotheses?
So I think, well, hallucination would hurt you in the sense, like it would mainly lead you to come up with hypotheses that were kind of, false positives that would show up, in this plot as like very, very light blue, which you kind of see a little bit of, like maybe this like homonyms thing is fake, but maybe it's not fake because like Claude came up with it and actually like came up with a description that worked well. But yeah, I mean, you could have hallucinations, but I think then like kind of the nice thing is having this way of formally testing the hypothesis, I think defends you quite a bit from hallucinations because you are like testing if they're correct. Yes.
Just to gain intuition, roughly how many collisions are you provided to start to get out interesting hypotheses?
Yeah, it's so I guess the number you get from the, like you kind of get like several thousand from the scraping stage, but actually can only fit like maybe like around 100 into the model's context. And resampling that didn't really lead to very different answers. So I think basically like maybe think of it as on the order of 100. Yeah. Okay. So let me move on to part 2, which is going to be about what I'm going to call statistical modeling with natural language parameters. This is kind of a nice conceptual framework that was developed by my student Ruiqi Zhong. So as a kind of starting point, let's think. So I'll talk about various statistical tasks near the end of this part, but as a kind of simple running example, let's think about binary classification. And so I'm going to talk to you about binary classification, where we're going to constrain the classifier to actually correspond to some discrete natural language description. So what is the task going to be? We're going to be given 2 data sets, D1 and D2. Our goal is to basically find the difference between them. So that's a binary classification task. But we want this difference to be expressed as a natural language strain H. And so this, kind of builds on a kind of line of work on kind of trying to use natural language descriptions as components of models, and including actually several by people here. So let me give you an example of what this task might look like. So here's an example of D1 and D2, where I'm giving you, 3 IID samples from D1 and 3 IID samples from D2. So given this task, what would be an H that would classify between these.
French.
Okay, good. So D1 is French. D2 is either not French or English. And so if you wanted to frame this as a comparative hypothesis, you would say, D1 contains more French sentences compared to D2. Okay, so that's good. I guess in general, the use cases will be somewhat more complex than this. So let me give an example of several use cases to just motivate, why this is useful. The first several will be use cases about understanding machine learning models. So the first might be, if I want to understand distribution shift, I might want to know what's different between my training distribution and my test distribution. And I might find out that the test distribution involves more formal writing than the training distribution. By the way, most of these are like actual outputs of the system that I'm going to present later. If I want to understand spurious cues in a data set, I could say what's different between the positive class and the negative class. And then, okay, hopefully one of the things that will come out is, the actual description of the classes. But if I find other differences that I don't think should really be diagnostic, those would be spurious cues. So if I find out that the positive class contains more URLs than the negative class, and my task is not counting the number of URLs, then I should worry about that as a spurious cue and maybe check that that doesn't actually influence a model's decision. Another thing is I could do automated error analysis. So, hand me two models like GPT-3 and TK11 billion, and I give it some task and ask, D1 is like the places where GPT-3 makes mistakes, D2 is the places where TK11 billion makes mistakes, and we can ask, okay, what's different between them? And then if I wanted to go beyond just understanding machine learning, say for like the social sciences, maybe I look at tweets from 2021 versus 2022, and find out that public opinion from this year is more optimistic about the pandemic than last year. Right, and so actually there's like many applications in say social sciences or other areas where these sorts of contrastive descriptions would be useful. So this hopefully motivates the task. So now, how do we do it? Well, I guess in some sense, basically the same way as before. I'm just going to say, okay, I have, I'm going to label everything from D1 as A and everything from D2 as B. I'll take a bunch of random samples from each of these data sets, put them in the context window of an LLM, and then just ask it, okay, what's the difference between B compared to A? And then I might get out a bunch of hypotheses. Note that the context window, as we mentioned before, is kind of limited to maybe 100 examples or somewhere on that order. So it might be small enough that I'm going to get some kind of spurious things, right? So some sample completions here are is more positive, contains the word chapter, is longer, is more positive is the true thing. Contains the word chapter is true of actually 2/3 of A just by chance. So that's why it's coming out here. And then is longer, well, that ends up being true, but maybe isn't what we cared about. So you kind of get these. And then we want some way of figuring out, okay, which of these are true, right? Because now actually you do have hallucinations, or okay, this isn't really a hallucination, but at least you're going to get some things that aren't right. So how can we test which of these really are right? Yes,
And
Jacob.
you're just generating these all in one shot. You're not like generating one and then projecting out that feature.
We are, you can do that. You don't need, this task is simple enough that you don't need to do that. But for some more complex tasks that I'll get to, you do. I guess the thing that you are doing iteratively is like, we're gonna like sample the A's and B's many times. Just because there is enough statistical noise here that you kind of want multiple samples. So it's not iterative, but it is multi-shot. So then we get this, somewhat long list, maybe like a couple dozen candidate hypotheses. And in this case, actually, many of them won't be correct. So we do need a way to filter them out. So again, we kind of fairly straightforwardly did the first two stages of the statistics pipeline. The data was already there for us, so we didn't even have to do anything for that. And then we just prompted GPT-4 to ask how they're different. So now how do we do these second two stages? So how could I sort of, quantitatively formalize what it would mean for one of these descriptions to be good? Any ideas? Yes.
You can use it to quantify the test set and see how well.
Great. Right. So basically, we'll say, okay, a good hypothesis helps tell D1 and D2 apart. So we're just going to give kind of random samples from either A or B, where the model is blinded to which one it was, ask it to classify it according to H, and then see what its accuracy is. And it turns out we need to do something a little bit subtler than that, because many hypotheses are comparative, that like A's are more, have property P more than B's. So so to formalize the comparative thing, I guess we're going to do a little bit of natural language semantics. Probably not enough to make Jacob happy, but enough to make other people sad. So hopefully it's a good middle ground. So let's take an example. Say H involves more formal writing. So this is comparative. We're going to interpret it as a 2-argument predicate, right? So we're going to interpret it as a function H that takes in sentences x1 and x2 and outputs a truth value in 0, 1. And the truth value is the value of, it's basically the truth value of this sentence, which is, quote x1 end quote, involves more formal writing than quote x2 end quote, right? So basically, this quoted sentence involves more formal writing than this other quoted sentence. That has some meaning under the denotational semantics of natural language. In principle, we could figure out this meaning by asking a person whether it was true or not. People might disagree, so maybe actually you take an expectation over people. But we'll ignore that and just imagine we have this function H, and we'll say H is a correct hypothesis about D1 versus D2 if the expectation under random samples x1 from D1 and random samples x2 from D2 of H of x1, x2 is much less than 1/2. Yes. Right. Sorry. Yeah. So I think you. Yeah. Sorry. So you would want to symmetrize here, and that's a good point. I actually kind of am missing that from this definition. But anyways, we do that. So right. So why much less than 1/2? Well, 1/2 would be random guessing. 1 would be if you were exactly wrong every time, which I guess would sort of be good, but 0 is like if you're exactly right every time. And then how to implement H? Well, I said you could do it with humans, but humans are expensive. LLMs are about 1,000 times cheaper than humans. So we're going to query an LLM and just ask an LLM, is this true? And this costs, if you take enough samples to get good statistical power, you end up having to spend about 7 cents per hypothesis if you use GPT 3.5 Turbo. So not nothing, but you can do a lot of hypotheses at 7 cents per hypothesis. For a coffee you can get, maybe 50 or something. Maybe in Cambridge coffee like 100. Okay, so this is what we do. So right, this overall system, we first have this proposer that generates a bunch of hypotheses. Then we have a verifier that kind of verifies these hypotheses by doing this sampling. There's also a step of doing false discovery rate control that isn't you want to do this because you're doing multiple testing. This isn't that important for these purposes. I think the 2 important things here. First of all, is why is this decomposition good? Well, the proposer can only see 30 is out of date. Now it's like 100 or so, but it can only see about 100 examples in the context window. Whereas this verifier can see thousands of examples, right? Because you can look at them one by one. You can just verify them in a loop. So that's why this is a kind of powerful decomposition. The other thing is you can steer the proposer based on some domain use case you care about, right? So if I if this is like some biomedical setting and I want hypotheses that are like relevant to patient health as opposed to the style of the doctor's notes, I can just add that to my prompt, and this will help steer GPT-4's proposals. And so, again, just like in the past section of the talk, you kind of get this nice steerability, right? So basically, in general, why do you want language? Well, interpretability or explainability is one, but then I think steerability is the other really big one. So let me just kind of give you example use cases that you can get from this system. So first, for understanding machine learning, I talked about this idea of using spurious cues, asking what's different between the train and test set. One that I think is maybe my favorite is there's this data set that's on subjectivity analysis. So basically, given a claim, classify whether it's an objective or subjective claim. If you put the two classes into our system, you get that the subjective class is a quote from a film review, and the objective class is a plot summary of a film. And we initially thought that this was like an error in our pipeline, but it actually turns out to be correct. So we went back and read the initial paper that curated this data set, and actually basically just said, well, we don't know what is objective or subjective, but we're pretty sure film reviews are subjective and plot summaries are objective. So those are going to be our two classes. And then, everyone forgets this and just calls it the subjectivity data set, but it's actually the film review versus plot summary data set. Another one, so this is a pretty famous one that was well known before, but is kind of reassuring. There's kind of a well-known spurious cue on the MNLI data set related to negation that we recover. And then on the spam classification data sets, it says that spam has a high number of hyperlinks. And we actually checked that if you fine tune a model on this data set and then feed it in, take some of Ruiqi's emails that have URLs in them, they all get classified as spam. So this really is a spurious cue. We already talked about automated error analysis. And then if we go beyond understanding ML, there's many other applications. So we actually curated this data set of 675 potential use cases. Our system doesn't work on all of them. But I think we think of this as sort of like a challenge set for people who want to use natural language systems for explainability. You have, almost 700 data sets that have kind of, unknown unknown differences between the two classes and domains of relevance. And so you can just, you can try and see what you can get out of this. To summarize, I guess I'll go beyond binary classification on the next slide, but maybe to summarize this particular classification system, right? We again have this 4-stage pipeline: initial data, generate hypotheses, formalize hypotheses, and then test on new data. So any questions before I move on? Yes, Jen.
Yeah, I guess this is related to, the PCA algorithm. In general, what distinguishes the one data set from the other is not going to be a single predicate.
Yep.
I'm just curious, firstly, does GPT or whatever, is it able to generate predicates fairly well, conjunctive, disjunctive? This also reminds me a little bit of the work in explainable ML where they learn local linear approximations to some kind of network classifier. I'm wondering whether you can run things with those data sets and see whether it also works. I don't know, of course.
Yeah, so those are all good questions. I'm not sure how linguistic conjunctions and disjunctions. My sense is GPT-4 isn't that great at disjunction, but I don't know.
It's interesting because you're sampling multiple hypotheses, right? And just
Right.
wondering whether
Yeah.
those are disjunctions or.
Okay, yeah. So the different hypotheses are often getting at different aspects of the data, and so actually maybe this is good motivation for the next slide, which is kind of the extension of what if we want to go beyond just this single language predicate. And so we can actually do this in some sense fairly straightforwardly, because the only thing I used was that I had this denotational semantics that lets me take a natural language predicate and turn it into a function, right? So let's ignore the comparative part and just think about one argument predicates, although you could generalize, right? So given any natural language predicate h, I could define bracket h to be the semantic denotation of H, which maps some, input X to the truth value of whether H is true of X. And so this means basically any natural language predicate can become a feature in a model. And so, if I have a bunch of features H1 through HK, I could define an exponential family model given weights W1 through WK, which is just P of X given WH is, E to the W1 H1 of X up through WK HK of X, right? So basically, given natural language predicates, I can just use them as features. And so you can actually think of this, you could think of this as an exponential family. I actually think it's maybe a little bit more correct to think of this as a one-layer neural network, where the encoder part of the model are these natural language predicates, right? I'm actually sort of doing feature learning here, trying to find these H's, but I'm constraining them instead of being neural representations to be natural language utterances. And so, once we have exponential families, we're kind of off to the races because you can start defining other things. So just to give an example of something, I guess maybe this gets a little bit at disjunctions. We can do clustering. You can also make this multimodal. So we could say, okay, I have dogs and elephants. I want to understand how their backgrounds are different. So please come up with clusters such that the base rate of dogs and elephants in these clusters are different. And so then you kind of get that, okay, dogs are more likely to have white backgrounds, elephants are more likely to be in the jungle. This isn't like that great of a system. Like I think this dog is in the jungle. Probably jungle really just means green background to this model. But you can get this kind of more complex stuff that is doing disjunctions, but maybe doing it via some outward statistical modeling rather than relying on GPT-4's ability to do it. Maybe one final thing, just like another example of cool stuff you can do with using language models as explanatory systems is you can also try to explain the internal representations of models. So I won't go into this, but just maybe a teaser for some very recent work we did on kind of trying to interpret clips internal representations using language. You kind of get nice kind of text back principal components for each attention head. So for instance, like layer 22 head 8 is about photos with the letter V, and you can kind of see at least, I guess there's some important caveats about whether this generalizes to the bulk of the distribution, but at least if you look at the top images, they're all V's. And so there's kind of, I think there's a lot of room to do cool stuff here. And again, this is, we're not the only people who've done this. There's other concurrent and previous work that does this, but I think this is a very cool area. So maybe I'll stop there and take questions. Yes.
I have sort of two related parts questions. So one is that thinking especially about the first part of the talk, you were effectively using, at least thinking about text tuning, you were using more capable models to sort of understand and sort of critique, in a sense, less capable models, right? So just so Roberta didn't have, and presumably it has fewer collisions than looked up in terms of the event.
Yep.
And I guess the question that arises is that, the broader picture that you painted at the very beginning of the talk was sort of the virtuous cycle. But at the very, in the sense that there's going to be, in any particular moment, a most capable model, let's say.
Yep.
And do we know that, can we actually do this process to actually have the most capable model unique itself? And if we can't, doesn't that sort of, would you be concerned that the sort of virtuous cycle picture that you were aiming for wouldn't arise? Well, I'll just ask the second part.
Okay.
You can answer both. The other part of the question is, so you use GPT-4 in an entirely black box way, and do we have any way of thinking about how much we're losing by not being able to use access to internal representations in any part of the pipeline that you're laying out here?
Yeah, so I think those are both great questions. So the first is, I'm generally using larger models to understand smaller models. Can we, like change that? And if not, should we like how sad should we be? And the second is, is there anything we're missing out by only having query access to GPT-4? So for the first question, I mean, I definitely would like us to get to a point where we can use smaller models to understand bigger models, or at least comparable size. Now, what are reasons to think there's room for progress there? I think one is, I think that is a big challenge. I think reasons to think there's room for progress, these models are sort of like mostly totally zero shots. And so I think there's a lot of room to specialize models to be good at the sorts of tasks we're asking them to do here. In fact, I think these tasks are particularly good fits for like fine tuning and specialization. Why is that? Well, I can generate many, like, statistical data analysis is an extremely broad umbrella. So I can generate lots and lots of data that are examples of statistical data analysis problems to fine tune on. And so I probably could hope to do, get significant performance gains. I think another thing is, for instance, like Distiller Roberta and Clip, I think they're actually comparable in parameter count. It's just that Distiller Roberta is again specialized to text. It is trained on a lot more data as well, so I think that's an important confounder. But like, specialization actually, if I'm like very specialized to knowing about a certain type of thing, I might be able to find errors that a more general model makes. I also have a lot of control over these models, right? Like I can look for contradictions. Like you could have a model debate a copy of itself and like look at the debate transcript. So I think there's a lot of room to get to places. I think the amount of distance we have to cover is quite large. So whether we get there is another question. I think even if we couldn't totally get to frontier models, I would still think there was value in this because some stuff will generalize and it wouldn't give you the virtuous cycle, but it would get you some level of comprehensive understanding. And then to answer the other question, I think we are losing a lot by not being able to fine tune GPT-4. I'm not sure how important to me the internal representations are for this task. I mean, for other tasks I would care, but I think fine tuning is the bigger thing. Other questions?
You can't do the topic model without log prompts.
Oh, sorry. Say that again.
Idea. The thing you showed towards the end, don't you need log prompts for that, or would you not?
Oh, no, because we're just extracting binary features like yes, no. Although also we're not using GPT-4 there, we're using GPT 3.5, although that also I don't think has log prob. But yeah, the log probabilities are coming from these like the log probs are coming from the exponential family weights. So these are 0, 1. So that part is okay. Yeah.
Because you also could do like a product of
right. So then you would want log probs, and yeah. So I think you are, generally speaking, I think you're losing something by not having log probs. I would agree with that. Yes.
So when using larger models to judge the hypotheses, what are the nature of your problem? I mean, for example, the larger model tells it's true, but it's not.
Right. So you're protected a little bit from this in that if the model is just bad, then you're going to get, like if it's bad at random, you will get false negatives rather than false positives, because you propose this hypothesis, but then your model doesn't interpret it correctly. So the hypothesis looks like it's a bad one, even though it's a good one. I think the bigger problem is if you kind of have correlated errors between the proposer and verifier. In fact, I think a great example of that would be this here, right? Where probably what the model means by jungle is actually green. And so you have this proposal that jungle is the discriminative feature. Actually, like green background is probably the true discriminative feature that it's using. But because both the proposer and the verifier are like have the same kind of like coarse graining mistake, it happily thinks it's good under the pipeline. And so I think that would be maybe the sort of false positives that you should worry about here. Maybe also some like steganography related stuff. I think, yeah, I think it's unclear how big of a problem that is. I think it is important to think about. Okay.
Thanks again.
Well, thank you.